Hello everyone, welcome to Powertronics and Instrumentation class. In today's video, we are going to discuss digital voltmeters. Now you are already familiar with analog voltmeters. Analog voltmeters, you have a circuit with you, you are familiar with it. You are using these analog voltmeters in your labs. You have an analog voltmeter with you. What are you going to do? You're going to connect it across a circuit. And how are you going to take the reading? You turn on your circuit, your voltmeter pointer is going to start deflecting, and once the two torques become equal, you're going to get a particular reading, and you need to look at it. It's going to take some time, and then somehow or the other you take the reading. Now, this particular procedure can be made easy when you're using a digital voltmeter. You don't have to think about whether you'll get the reading wrong, because it's going to be a digital display. You just have to make sure that you write down the reading without making any mistakes. That is, instead of 1, don't read it as 7, or instead of 7, don't read it as 1. That's the only thing you need to be afraid of, right? So digital instruments are more convenient, it's error free, it's accurate, it has higher precision, it has a lot of advantages. Now let's see what is the working of the digital voltmeter. Now in the digital voltmeter, you can measure AC or DC voltages. The voltage range that can be measured is plus or minus 1 volt to plus or minus 1000 volt. So you can see you have a high range value that can be measured. Okay. Now, how are you going to measure the voltage? You have an unknown input voltage. It is sent to a pulse generator. The pulse generator is going to produce a pulse which has a width corresponding to the magnitude of the input voltage. Okay, the width of the pulse generated from the pulse generator is going to be proportional to the magnitude of the input voltage. Then, as mentioned before, this pulse is going to be compared with a predetermined clock pulse. It's going to be given to an AND gate, and then you're going to convert it into a negative train using the NOT gate. You're going to count the number of pulses, and correspondingly you will get the magnitude of the input voltage. So the basic concept is that the pulse generated from the pulse generator, the width of the pulse generated is going to be proportional to your input voltage. And based on the type of analog to digital conversion, you have 4 different types. We will be studying 3 different types in detail. You have the ramp type, dual slope integrating type, and the potentiometric type and integrating type. Let's move to the first type of digital voltmeter. You have the ramp type digital voltmeter. And the ramp type digital voltmeter, you are having a ramp signal, and this ramp signal is continuously being monitored. And you can see that this particular line, it is the unknown voltage signal. Now you can see that continuously it is being monitored, and when your ramp signal coincides with the unknown DC or unknown voltage signal, a pulse train starts to begin. You can see over here, once the ramp signal coincides with your voltage signal, a clock pulse or pulses are starting to get formed at the output section. And the clock pulses will stop once the ramp signal reaches 0. The clock pulses will stop when the ramp signal reaches 0. Okay, and according to the number of pulses present during this particular duration, according to the number of pulses present during this particular duration, you can find out the magnitude of the voltage. Suppose your voltage was a higher magnitude. You can see over here that the number of pulses would be higher. And suppose your voltage was of a lower value. You can see over here, this would be your first coincidence point, and your number of pulses would have become 3. So I think from this graph itself, it is understood that the number of pulses are determining the value of your voltage signal. We have a simple block diagram over here. You can see that the DC input voltage, it is converted to a range which is compatible with our particular signal. We know what is the scaling factor over here, so it's not a problem. And you have a ramp generator. Your ramp generator is being compared with the DC value, and the pulses will start to begin once the ramp signal becomes equal to the DC value. And when will the pulses be stopped? The pulses will be stopped when your ramp generator becomes 0. When your ramp generator becomes 0, the pulses are going to stop. And correspondingly, you will be counting the number of pulses and you will be getting the corresponding voltage value. So this is quite simple, right? Although the block diagram seems large, it is quite simple. Next, we are going to study the dual slope integrating type digital voltmeter. Now, over here you are having, over here you are having a particular analog voltage and you are sending this analog voltage to an integrator. Now, you know that if you are giving a particular value to an integrator, it will start increasing. And the slope of the integrator, it is proportional to the value of the voltage signal. Okay, the value of the slope or the slope of the particular integrator, it is going to be proportional to the value of your output voltage. And you are going to keep, you are going to send the input, the unknown voltage signal to the integrator for a particular time t. It's going to be kept in this particular time t for a fixed duration. And once the time t has reached, you are going to switch the input of the integrator. You are going to change the input to the integrator. It's going to be a reference value of minus V reference. The reference value is known to us, and that is why, since we know the value of the reference, the slope is also known. And the slope is going to go downwards because you are giving a negative reference voltage. And because the slope is known to us, we also, the slope is known to us, right? Now, I'll just mention a particular point. Suppose the value of the input was higher than this particular example given over here. Okay, suppose the value of the input, okay, the input voltage was higher. You're going to keep the input voltage as the input to the integrator for a particular time t. Okay, so it is going to be kept for this particular time t. If the value of the input was high, you can see that the slope would have been more steep. And the height of this particular point would come up to here. But you can see that the reference input has not increased correspondingly. The reference input is the same, and that is why the slope will be the same. This slope will be the same, so you can just draw a parallel line over here. Okay, the slope would be the same, right? The slope is the same, so you're just drawing a line parallel to this particular point. And you're going to see how much time is going to take to come from this peak value to 0. So you can see over here for your first case, this was your time. But for your second case, the time has increased because the value of the voltage was higher over here. And according to the difference in this discharge time, you can find out the value of the input voltage. And you have a relationship. The input voltage is given by the reference voltage V reference into T divided by capital T. So if the magnitude of the input voltage was high, T would be greater, and this equation remains same. Now you can take another case also. You can just assume that the value of the input was low. Suppose the same time duration, right? The value of the input is low. So your slope is going to be a bit less steep. But the discharge rate is the same because the reference value is the same. So you just draw a line parallel over here. You can see that the time for it to reach 0 is less. Okay, so this is how you are going to find out the magnitude of the input voltage over here. You have two slopes. One of the slope, the first slope, we do not know. The first slope will be varying. It is varying according to the value of the input voltage, but it is kept in that particular, it is turned on for a particular time t. And then once it reaches the particular time t, you are going to switch the input to the integrator. You are going to change the input to the integrator. You are going to give a value of minus V reference. And now you are going to measure the time taken for the slope to reach from the peak value to 0. And correspondingly, you will find the output. The output is given by VA is equal to V reference into T divided by capital T. Okay, it's quite simple, right? The working principle is quite simple. Next, we have the integrating type. It is quite similar to the dual slope integrating type. And the fourth one, potentiometric type digital voltmeter. In potentiometric type digital voltmeter, you are comparing a reference voltage with your unknown voltage. Okay, you can just see the block diagram over here. You have an unknown voltage over here and you have a reference voltage over here. You are going to do a comparison, and if they are not equal, an error signal is produced, and you will adjust the potentiometer sliding contact such that the error becomes 0. So a comparison is taking place all the time. Okay, suppose an error is there, the sliding contact will start moving such that it will start moving until the reference voltage and the unknown voltage become the same. And when the error becomes 0, the sliding contact position will become constant, and you are going to find out a comparison has been made, the error has become 0. So your unknown voltage will be equal to the reference voltage and you will be getting the particular output. Okay, this particular portion is quite simple. You are just comparing the unknown voltage with the reference value. If it is not equal, it is sent to an error amplifier, and this will be controlling the sliding contact of your potentiometer device. And it is changed. The sliding contact is changed until both of these voltages become the same. And when they become the same, we know it is a reference voltage, right? So we can find out what is the value of the unknown voltage by simple comparison. So this was the potentiometric type digital voltmeter. Now, for all of these voltmeters, how are you going to select the range of the particular display? That is mentioned over here. This is the last topic of the digital voltmeter. How are you going to select the range of the display? You can see over here this particular magnitude over here. It is the first decimal or number of your display. It can represent 0, 1, 2, 3, etc. Now, you are having a number of resistors over here, and you can see when only one resistor is connected, that is when none of the resistors are there, it is representing the 2 volt. If one resistor is present, it represents 20 volt, and when all three, when the 2 resistors are there, it represents your 200 volt. Okay, so this is actually dividing the voltage range. Now, whenever your voltage is less than 2, or if it is 1.999 volt, you can see that you are having a particular switch. You can see over here you are having a particular switch over here. When your particular voltage range is 2 volt, your decimal input, you can see that this is actually an LED display. All of these are LEDs. Okay, the LED will get powered when it is connected to this particular switch. Okay, so when your input voltage is in the range of 2 volt, the switch is placed in the first position, and your LED which is in the first position, it will be getting connected to the particular source. Okay, so actually the source connection is given over here. It will be getting the circuit will become closed when the switch moves to the position number 1. Okay, so 1.99 volt means you have 1 over here, right? It can be 0, 1, 2, 3, etc. Right? So you have 1 over here, and when your switch is in position 1, this LED will get turned on. Now, if your voltage range is of 19.99 volt or less, if your voltage range is of 19.99 volt or lesser than 19.99 volt, your switch will be moved. This position will be moved over here. So your arrow will move over here. Correspondingly, this switch will get moved to position number 2. And you can see over here, this LED will get turned off. So what will it display? It will show 1.99. This decimal gets turned on, and this will be your particular output. So you can measure voltage ranges up to 19.99 volt. Finally, when it reaches, if it is 199.9 volt or less, your switch will move to third position. Correspondingly, this switch will also move to the third position, and this LED will get turned off. It will turn on the third LED. So this is how you are going to change the ranges in the same display. Okay, in order to change the display, all you have to do is place 3 LEDs. If your switch is in the position 1, the remaining 2 LEDs are off, and the only one LED is turned on, giving you a range of 1.999. Then when the LED is in position 2, 19.99 volt up to 19.99 volt can be measured, and then this is for 200 volt. This is the range selection process that takes place in your digital voltmeter. So in this particular video, we have gone through digital voltmeter, different types of digital voltmeter. You have the potentiometric type digital voltmeter, the dual slope integrating type voltmeter, the ramp type digital voltmeter, and then finally we found out how the range selection is taking place in your particular digital display. So I hope this video was useful. Please stay tuned for more videos. Thank you.